This video serves as an introduction to chemical reactions, as well as how to identify the different types of chemical reactions and what's expected of you to know about each of the different types of chemical reactions. So there are 5 types of chemical reactions, and they are synthesis, decomposition, single replacement, double replacement, and combustion. What's expected of you is you need to be able to look at the balanced equation or an equation for a chemical reaction, balance the equation, and then determine what kind of chemical reaction it is. Additionally, and we'll talk about this later on, for 3 of these 5 types of chemical reactions, you should be able to predict what the products of those reactions will be. You have enough knowledge to do that. So synthesis reactions are the first one we'll start with. They're the easiest one to identify. Synthesis reactions occur when 2 or more reactants combine together to form a single product. So if this reaction was a picture, you would say the gold reactant and the green reactant combine together to form the compound gold-green. Gold and green could either be atoms, they could be small molecules combined to form a larger molecule. It's also written in the format A plus B yields the compound AB. The synthesis reaction is easiest to spot for one reason and one reason only. It is the only reaction type where there is one product. So if you look at a reaction, you see only one product, it is definitely a synthesis reaction. You're familiar with synthesis reactions because synthesis reactions are things like the formation of water. So for example, if I were to write the equation 2H2 plus O2 gives me 2H2O. Notice that my reactants are hydrogen gas and oxygen gas, and they combine together to form one product, and that one product is the compound water that we all know and love. So that is a very simple synthesis reaction. Decomposition reactions are the opposite of synthesis reaction. In a decomposition reaction, one reactant falls apart into 2 or more products, usually with the introduction of something like heat or electricity or a temperature change of some kind. But you start with one reactant and it falls apart into 2 or more products. Once again, if we represented this in pictures, it would be the compound gold-green falls apart into the compounds, atoms, or molecules gold plus green. And we write this as AB falls apart into A plus B. These are also very easy to spot. Decomposition reactions are the only reactions where there's only one reactant. So these are very easy to spot if you just see one reactant. And an example of this is the breakdown of magnesium oxide. Magnesium oxide is the compound MgO. And if you heat it or let it take its time, it will actually fall apart back into pure mercury and oxygen gas. And that's also a balanced equation. Otherwise, single replacement is got a very long definition. And when you go into the next little bit on the activity series, you'll understand more about it. But basically what this is a reaction that occurs when one compound reacts with an element or diatomic gas, and that element or diatomic gas steals the partner in the compound to form a new compound and a new single element or diatomic gas. So it will look something like this. So if we were to draw our molecules again, we have the compound gold-green and the single element or gas, which is blue. Blue can either replace gold to form the compound blue-green, leaving gold on its own, or blue can replace green, leaving the compound gold-blue with green on its own, and it's written as either AB plus C gives you AC plus B, or CB plus A. Notice there is a reason that I drew this and wrote this way. If you remember anything about ionic compounds, remember that this compound right here, which is this one, is always consisted of a cation bonded to an anion, which means these compounds also have to be a cation bonded to an anion. In this case, it's entirely dependent on blue. If blue is a nonmetal, it's going to be the anion. And if blue is a metal, it's going to be the cation. So you have to know what blue is to know which partner blue is going to replace. The best way I like to think about the single replacement reaction is I like to think of it as the steal your boyfriend / steal your girlfriend reaction. These two atoms are in a couple, and they might be a happy couple, they might be an unhappy couple. But this better prospect comes along and is able to steal the boyfriend or girlfriend from a couple, making a new couple and a single person. But once again, it all depends on what the single gas or the single metal or non-metal are made of as to whether or not the single replacement is going to happen and how it's going to happen. Single replacement reactions are governed by something called the activity series, which we'll look at a little bit more in detail later on in this unit. I do want to show you two quick examples of single replacement reactions. The first is the reaction of the compound HCl, which is hydrochloric acid, with potassium. Potassium is a metal, and therefore it can form a cation, which means in this compound you have the hydrogen cation and the chlorine anion. So the potassium is going to replace the hydrogen, leaving you with potassium chloride and this diatomic or two-atom hydrogen gas. In the second reaction, you have sodium bromide, in which case, remember the cations first, so sodium is the cation, bromine is the anion, and you have fluorine doing the replacing. Since fluorine is a nonmetal, it forms an anion, therefore it's going to replace the bromine, and you're left with bromine gas, this Br2 diatomic gas on its own. I do want you to see that anions replace anions, and cations replace cations in single replacement reactions. In a double replacement reaction, which is the next type, this happens when two ionic compounds react, and the compounds swap partners. Remember, though, that it has to always be an anion bonded to a cation in both cases. So it would look something like this, where the compound gold-green reacts with a compound blue-red to form gold-red and blue-green. If you think of it this way, the gold and the blue are the cations, so they stay first. The green and the red are the anions, so they go second. And the anions just swap places on the same cation. It's written as AB plus CD, gives you AD plus CB. Double replacement reactions only happen between ionic compounds. So what happens is the ionic compounds are actually put in solution to make something called an aqueous solution. When ionic compounds are dropped into aqueous solution, they actually fall apart. So what would end up happening in this case is you kind of would have free golds, free greens, free blues, and free reds just kind of floating around. And that's how they're able to find new partners, is because they're just kind of swimming freely in this water-based solution. What ends up happening sometimes in a double replacement reaction is that one of the new compounds that form, whether it's AD or CB or, gold, red, green, blue, actually is no longer soluble and forms a precipitate. And we'll talk about this a little bit more when we get into predicting the products of chemical reactions. So these are two examples of double replacement reactions. Notice how you have an anion and an anion and a cation and a cation, and they just end up swapping places in both cases. Same thing with the second reaction, although it's a little bit more complicated. One of the really important things that you need to know when you write the products of double replacement reactions is you need to remember how to write the formulas for ionic compounds, because all of these subscripts that appear, they're all determined by the charges on the ionic compounds. The last type of reaction is completely different than the other four. The last type of reaction is called combustion. A combustion reaction is the burning of a hydrocarbon and oxygen gas to form carbon dioxide and water. It always looks like this. So notice that I wrote CXHY, and occasionally there may be an O on here, which would be right here as well, but not necessarily. This is a hydrocarbon, and these X and this Y can literally be any number. What is true about a combustion reaction is you're always going to have oxygen as the other reactant and carbon dioxide and water as your products. They're really easy to spot. The products are always the same. One of the reactants is always the same. The only thing that makes these hard is that they're sometimes tricky to balance. So you need to be able to understand what how to balance these, and usually that trick of doubling the odd number works on the most difficult of combustion reactions. So finally, what do you need to know about all of this? The biggest thing is if you see a reaction, you need to be able to identify what that reaction is simply by looking at the equation. Of course, you're also going to be expected to balance the equation, but you should be proficient in that by now. Finally, for combustion, single and double replacement, you should be able to predict the products of the reaction. Combustion is easy because it's always carbon dioxide and water. The others are easy if you know how to write formulas for compounds. Finally, there's a little bit in the PowerPoint on state symbols. So just take a look at those state symbols and understand what they are and what they mean as you continue through this unit. As always, keep practicing these problems. The more you do at this, the better you'll get. Finally, there's a worksheet on this. It's just for practice and the answer keys in Schoology. However, there is that lab we did last class, which you can now identify the reaction types. And when you're done with that lab, hand it to the sub.